What specific problem does the proposed order-preserve-RAG method aim to address in the context of long-context LLMs, and how does it differ from the traditional RAG systems?
The proposed order-preserve-RAG method aims to address the issue of answer quality degradation in long-context LLMs by preserving the original order of retrieved chunks from the text, rather than arranging them in a relevance descending order as traditional RAG systems do. This approach recognizes that the sequence of information can significantly impact the model's ability to generate accurate answers. Experiments show that while traditional RAG may lead to confusion due to irrelevant or distracting information when too many chunks are retrieved, the order-preserve mechanism enhances answer quality by maintaining contextual coherence. Specifically, the order-preserve-RAG outperforms traditional RAG, achieving a higher F1 score, 44.43, with fewer tokens compared to LLMs without RAG, which struggle with larger input sizes. Thus, the key difference lies in the handling of chunk order, which is crucial for optimizing the retrieval process and improving overall answer quality.
How does the proposed order-preserve-RAG algorithm work? Please illustrate the step-by-step process of how chunks are retrieved and utilized in generating answers from the original context.
The proposed order-preserve-RAG algorithm operates by first splitting the long textual context denoted as D into n sequential and uniform chunks, C_I, where the index I indicates the order of the chunks in D. When a query, Q, is presented, the algorithm computes the relevant score for each chunk, C_I, using cosine similarity between the embeddings of Q and C_I. It then retrieves the top, K, chunks with the highest similarity scores, preserving their original order in the document rather than rearranging them by relevance. This order-preserving mechanism allows the model to utilize the context in a way that maintains the narrative flow, which is crucial for generating coherent answers. Finally, the retrieved chunks are used as context for the LLM to generate answers, balancing the amount of relevant information while minimizing distractions from irrelevant chunks.
Can you provide a simple example to demonstrate the inner workings of the order-preserve-RAG algorithm, detailing how the relevance of chunks is assessed and maintained during the retrieval process?
The order-preserve-RAG algorithm operates by first splitting a long document into sequential chunks, denoted as C_I, where the index I indicates the order of the chunks in the original text. When a query, Q, is presented, the algorithm assesses the relevance of each chunk by calculating the cosine similarity between the embeddings of the query and each chunk, retrieving the top, K, chunks with the highest similarity scores. Unlike traditional RAG, which arranges these chunks in descending order of relevance, the order-preserve-RAG maintains the original sequential order of the chunks from the document. This approach ensures that the context remains coherent and relevant, as the model can leverage the natural flow of information in the text. For instance, if the top retrieved chunks include C_2, C_3, and C_5, the order-preserve-RAG would present them as C_2, C_3, C_5, rather than rearranging them, thus enhancing the quality of the generated answer.
What are the theoretical and practical benefits of using the order-preserve-RAG method compared to traditional RAG or long-context LLMs without RAG, in terms of efficiency and answer quality?
The order-preserve-RAG method offers significant theoretical and practical benefits over traditional RAG and long-context LLMs without RAG. Theoretically, it preserves the original order of retrieved chunks, which enhances the contextual relevance and coherence of the generated answers, leading to improved answer quality. Practically, our experiments demonstrate that order-preserve-RAG achieves higher F1 scores, such as 44.43 with Llama 3, 1-70B using only 16K tokens compared to 34.32 and 32.36 F1 scores from Llama 3, 1-70B and GPT-4o, respectively, when using the full 128K context without RAG. This indicates that order-preserve-RAG not only reduces the input length, but also maintains or enhances answer quality, making it more efficient. Additionally, the method effectively balances the trade-off between recall and precision, optimizing the amount of relevant information while minimizing distractions from irrelevant data.
How was the order-preserve RAG method validated in the experiments, and what specific metrics and datasets were utilized to demonstrate its effectiveness against baseline models?
The order-preserve RAG method was validated through experiments conducted on the N, QA, and EN, MC datasets from the INAFT benchmark, which are specifically designed for long context question answering evaluation. The effectiveness of the proposed method was demonstrated using the F1 score as the evaluation metric for the EN, QA dataset and accuracy for the N-MC dataset. Results showed that when retrieving a larger number of chunks, the order-preserve RAG significantly outperformed the vanilla RAG, achieving an F1 score of 44.43 with 128 retrieved chunks compared to 38.40 for vanilla RAG. Additionally, the order-preserve RAG also outperformed long-context LLMs without RAG, achieving a F1 score of 47.25 with 48K tokens compared to 34.26 with 117K tokens for the Llama 3.1-70B model. This validation highlights the method's efficiency and improved answer quality over baseline models.
What are the key results achieved with the order-preserve RAG method according to the experiments, and how do these results compare with both RAG and long-context LLM approaches?
The key results achieved with the order-preserve RAG method demonstrate a significant improvement in answer quality compared to both traditional RAG and long-context LLM approaches. Specifically, in the EN, QA dataset, the order-preserve RAG achieved a F1 score of 44.43 with 16K retrieved tokens, while the long-context LLMs without RAG, such as Llama 3.1-70B, only reached a F1 score of 34.32 using 128K tokens. Additionally, when comparing with vanilla RAG, the order-preserve RAG outperformed it significantly, achieving 44.43 F1 score versus 38.40 F1 score when retrieving 128 chunks. In the EN, MC dataset, the order-preserve RAG also showed superior performance, obtaining 88.65 accuracy with 192 chunks, compared to vanilla RAG's 81.22 accuracy. Overall, the order-preserve RAG not only enhances answer quality, but also reduces the number of tokens required, making it a more efficient approach than both traditional RAG and long-context LLMs.